In this video, we're going to see that all the hard work that we did in the previous video is going to finally pay off. We're going to be able to use the characterization of limit functions via sequences to prove several properties of the limits of functions. So we're going to be able to show the limit laws for functions, and we're going to be able to also show the standard theorem for limits of functions. So let's get started. The limit laws tells me that if I know that the limit as x approaches c of f of x is equal to a, and the limit as x approaches c of g of x is equal to b, then first we have that the limit as x approaches c of f of x plus g of x is equal to a plus b. That is that the limit of the sum is the sum of the limits if both limits exist. Then we have that the limit as x approaches c of f of x times g of x is a times b, so that means that the limit of the products is the product of the limit, again, if both limits exist. And last but not least, if I know that b is not 0, I also know that g of x is not 0 for all x sufficiently close to c. Remember, we only care about things that happen near c. So as long as g of x are not 0 near c, so we're making sure we're not dividing by 0, then the limit as x approaches c of f of x over g of x is equal to a over b, so the limit of the quotient is the quotient of the limits. I'm going to prove number 1. I'm going to leave 2 and 3 for you as an exercise, but they're quite easy to do. So here we're going to use, as I said, the characterization of limits via sequences. So we need to start with an arbitrary sequence such that the xn's are not c, and I know that xn converges to c. Okay. Then, using the characterization of limits via sequences, we have that f of xn converges to a and g of xn converges to b. Because remember, that is what that theorem told me, that if I know that the limit as x approaches c of f of x equals a, that implies that for any sequence that I pick that converges to c, f of xn converges to a in this case. Okay, so we have this. But then we can use what we know about the limit laws for sequences to finish a proof. You see, if we apply the sum rule for limits of sequences, this will imply, as we know, the limit of the sum of two sequences is the sum of the limits. So f of xn plus g of xn converges to a plus b. But now, this is true for any sequence that I pick, as long as I know that the sequence xn converges to c and xn is different from c. So, by the characterization of limits via sequences, this will imply that the limit as x approaches c of f of x plus g of x is equal to a plus b. As I said, I'm leaving proofs of 2 and 3 for you as an exercise, but as you can see, this is very easy to do if we use this characterization of limits via sequences. Of course, if you want, you can also prove this statement using the epsilon delta definition of limits. It's a nice exercise to do, so if you want to try it, you are more than welcome to do so. We also have the standard theorem for functions, and we will see that again we can prove this using what we already know for sequences. So we're going to assume that we have three functions, f, g, and h, defined on an interval ab except possibly at the point c, and satisfying that f of x is less than or equal to g of x less than or equal to h of x for all x in the interval a, b, except possibly at c, because remember, we don't care what happens at c. We're going to also assume that the limit as x approaches c of f of x is equal to the limit as x approaches c of h of x, and they're both equal to L. Then this will imply that the limit as x approaches c of g of x is equal to L. So again, we are just sandwiching the function g in between f and h and forcing the limit to be the common limit that f and h have, which is L. That is the idea. As you see, it's the same idea as we had for sequences. So how can we prove this? Well, we want to use the characterization of limits via sequences. So we're going to pick an arbitrary sequence such that all the terms are in the interval ab, the xn's are not c, and that xn converges to c. The first thing that I know is because the limit as x approaches c of f of x and h of x are L, then using this characterization of limits via sequences, I know f of xn converges to L, and also that h of xn converges to L. But we know more. We know that my xn's are in the interval ab. We know that xn's are not equal to c. And, well, because the xn's are in this interval ab, then we have that same inequality that was given in the statement of the theorem. So we have that f of xn is less than or equal to g of xn less than or equal to h of xn for all n. Oh, but now we have exactly the conditions that we need for the sandwich theorem for sequences. So by the sandwich theorem for limits of sequences, we know that then the g of xn converges to L. But xn was an arbitrary sequence satisfying that xn converged to c and that the xn's were not c. So then, again by the characterization of limits of functions via sequences, we know that the limit as x approaches c of g of x is equal to L. And that completes the proof of the sandwich theorem for functions.